Many of you know that with the North Dakota Corn Council's generous support and support from Pioneer Hybrid and also the International Plant Nutrition Institute, we've been working from 2010 through 2013 to gather enough field nitrogen rate studies in order to feel very comfortable with changing our recommendations. So the results will be out, the new recs will be out 2014, and I'll just kind of run through what they are. Is this supposed to do the thing on the front row too, Magician, or just the back ones? Do I have to crane my neck and find out what's happening? I can do this by heart, but it'd be better if I use the slides. All right, Magician's working on it. In the meantime, so our current published recommendations are yield potential times 1.2 lesser credits, and I really hate them, and there's reasons why I hate them. If you look at the line going up, that's the relationship between the N rate and the yield potential. You'll see that it's a straight line, goes through 0, 0. Some of you have made boo-boos, errors in the field before, haven't put on nitrogen in an area, and you understand that unless the temperature got to 115 degrees during pollination, you probably made some corn there. So it's not reasonable to that it goes through 0, 0. And that magic line up there is your wisdom in predicting what your yield's going to be next year. How many of you are really good at that? I'm not very good at that. I don't want you to be good at it. I don't like this at all. So anyway, what we've done is we've gathered a lot of sites. We've gathered 77 sites and taken them to yield in the state since 2010. Many of them are in the east, but a good number of them are also in the west. It's my imaginary friend, I guess. Okay, so, and then I also asked colleagues from the surrounding states and provinces if they could give me a hand. So John Hurd from Manitoba gave me 9 sites that are very recent, within 10 years from southern Manitoba. And John Lamb at University of Minnesota and Russ Severson at Crookston, they gave me 21 sites from northwest Minnesota that have been their N-rate studies from about 2005 to 2008. And then Ron Gelderman gave me some data from last year, and I used some of it didn't include in the data set. You do a statistical thing and figure out if it fits or not. So anyway, all these sites up there fit our data set. They reflect what the responses are on our soils within our data set. So the entire data set that I'm using in order to revise these recommendations are about 117 site years, all within, most of them from 2005, and the greatest share from 2010. So it's even a better data set than what I had with wheat when I changed the wheat recommendations here a few years ago. So thank you for the support. One of the things we wanted to know is our recommendations have shown and considered soil nitrate to 2 feet. And so we wanted to see what would happen if we didn't include those in our data set. And so this is what it looks like with all of those sites if we didn't include the soil nitrate. And you'll notice at the 0 N rate, on the left-hand side there, that the yields go from about 48 bushels an acre up to, what, way over 200 or something like that? I mean, is that reasonable to expect that no N is going to do that? And so there must be something else happening. Also, if you go to the other extreme, into the 200 plus N side, the yields are maybe a little bit higher than what you see the range over in the 0, but not that much different. So this is really pretty much a shotgun blast and is not very useful at all. So this is what it looks like with the nitrate test. There's still a lot of scatter, but it makes a lot more sense. You see that nice curved line in there? That's what we expect as soil scientists when we do fertility research. It's called the law of diminishing returns. The first increment of whatever nutrient you apply gives you the greatest yield response. Each increment after that gives you progressively less and less, and then you reach a point that's kind of the peak, and then you have things like green snap, increased disease, and standability problems where the yield actually goes the other way. So we're keeping the nitrate test, and so those of you that do soil testing for a living, you can stand relieved, I guess. So one of the things that we did with our wheat work, and it also makes sense here, is divide the state into general climate zones general zones that differ greatly by soils. And the dividing line in this state is West River. It's the Missouri River. So everything west of the Missouri River has two things that usually happen. One, it tends to be drier, or certainly it has a lot greater weather extremes than the east, but then the other thing is the sediments there are 65 million years old compared to somewhere around 10,000 or so to the east. So it's a natural dividing line. When I move the western sites out of the data set, it improves greatly the R-squared of both things, and so the West River will get a different recommendation set than anything East River. So this is what it looks like, still a lot of scatter, so you need to go further. So I went further. One of the things we found with the wheat was that farmers that are in long-term no-till, not no-till once in a while when they feel like or when it's convenient or they can't get a chisel plow in there, and so they just stick the crop in the ground. But people are serious about it and do it every year for a long time, and greater than 6 years. And we find that it has a more efficient use of nitrogen for reasons I don't have time to explain today, but it just does. And so we divided that out also. So East River, there'll be a different set of recommendations for fields that have a history of long-term no-till, one-pass seeding. So that's what we're going to do. So that's the rest of it, and it includes, this is, well, one of the things I didn't do on the wheat because I didn't have that many sites in the high clay, but I have a lot of sites in high clay, and it was very clear from 2010 and continued on that fields that are in high clay respond quite differently than those that have other textures, loams and sandy loams, loamy sand. It's just completely different as an efficiency loss that you have when you're in high clay soil. So dividing those out helps group things around the line, but it's still a lot of scatter, and so I started thinking about this. And in the wheat, I have things divided up into high productivity, medium productivity, and low productivity. Well, low productivity on this side of the river doesn't make a whole lot of sense because, if it really was growing 60 bushels every year, you'd figure out a way to plant barley or something in it, and either that or the person that farmed that farm after you got done with it would figure that out. So I figure that probably dividing it up into high productivity and the lower productivity, I don't say low productivity, but the lower productivity would be a better plan. And I played around with yields, and it seemed like for the data sets that about 160 bushels was a pretty good dividing line. So those sites that at least had one of the treatments went above 160 bushels, placed them into the high productivity data set. And the ones that never had any yields above 160 or over, those were in the other data set, the lower data set. So that's what I did, and here's what the higher productivity, those that exceeded 160 bushels, and you can see there's a lot of plus 200 bushels up there, and a lot tighter around that curve, so that makes a lot of sense. It's still, when you get to the right-hand side of the curve, you're still talking about peaks in the plus 300 pounds of N range, and we'll talk about that a little bit, but some of the others are even worse than that. So these are the sites that, I've talked about my problem children over the years since I've been in this project, and these include those. These are ones that have drainage issues. They're all high clay, but these have more drainage issues than others. And so for whatever reason, usually moisture related, they're a very poor efficiency of nitrogen, and the peak of that goes way over 400 pounds, which is another reason that rate really isn't a solution to these soils. So then the medium textured, I tried the plus 160, below 160, and it works for this too. And so these are the medium textured sites, and these are the stars. These are the ones that are most efficient of nitrogen of any of the cultivated tillage sites. And also the yields are spectacular, just incredible yields with these things. And so this should be a clue as we were going through there that old yield-based formula was just kind of insane, so we're not doing that. So here's our stars right here, and then this shocked me. When I went into the sites that were lower than 160 bushels an acre, I didn't see this. I didn't expect to see this at all. I see this in the high clays during our wettest years, but I didn't expect to see it with the medium textured soil. So obviously, in our loams and sandy loams and loamy sand sites, we have leaching issues and wet years and loss of N and very low efficiency of nitrogen. And I don't tell a whole lot of anecdotes when I talk, because I usually always try to show the data. But I think this is a good object lesson. I worked with a grower west of Walcott for about 4 years, a good young grower, and he side dresses every year, just always had, and his yields around our plots are 180, just high yield areas. So high water table, sandy loams. And we've had wet years, and in 2011 was our wettest year, and it was continuously wet from 1st of May through the middle of June. And so we're out there in this person's field, and the corn was yellow, and the corn was orange, and the corn was, I never saw blue corn before. There was blue corn and purple corn and every corn that you can think of color. And so I went back and I wrote a crop and pest report about rainbow corn and how, it was the water, and all this stuff. That was the field. We had a plot on that field. And a week later, we went back and visited the field to make sure it was still alive, and it was. And the farmer had just gone out. It was dry enough so he could go in and put his anhydrous on side dress. And I thought, the poor guy, he's not going to do anything. And it ended up making 180 bushels, something like that. But his neighbors, I don't know what his neighbors do. Do they go fishing after planting? Do they, visit the relatives in California? Do they just hate the guy and so they look the other way when they drive past? But how can you have this tall, green, really nice corn that's been side dressed, and then their corn is about as tall as this, and I'm sure that they'd already called the insurance company. The difference was just appalling, and I don't know why everybody in that neighborhood isn't side dressed, but there's a reason why these medium textured soils scream for side dress, and that's because of these losses that you get in the wet years. So anyway, these are candidates, and I didn't expect it to be this bad, but it certainly is. And so in addition to some of those high clay sites, I'm also going to preach very hard with these. So our old recommendations don't take any consideration for any economics at all. Doesn't matter what the price of corn was, doesn't matter what the price of nitrogen was, 1.2 times your crystal ball yield, and that's the rate that you're going to use. So we're going to trash all that, and the reason why is, there's lots of reasons. The other reason is because those recommendations don't take into account any economics at all. And so with this system called the Return to N, it was developed by John Sawyer, who was just in Fargo last week at another conference, and Emerson Ziegler from Illinois. They devised what the economists call an economic production function, where you take into account the response of a crop, the increase in yield to the response of an input, but then you also consider the cost of the input and the price that you get for the commodity. So those of you that remember your college or high school economics, it's that marginal return thing. You remember that? Kind of clicks. You kind of use these things from time to time. You just don't go to school for fun. At least you're not supposed to. So anyway, this is what the background will look like. You're not going to see this, but when you see the charts and the circulars, the background is going to be the peaks of each of these curves. Each one of those sets of curves, or arrays, A-R-R-A-Y, arrays. Each one of those arrays, it goes from, the bottom one is $3 corn, and then $4 corn, $5 corn, $6 corn, $7 corn, $8 corn. This is just an illustration for you to kind of visualize what's going on. And then within the arrays, the bottom line is $1 a pound N. Yes, Virginia, we've received $1, we paid $1 a pound of N since I've been at NDSU. And each one of those lines is a 10-cent difference. So it's $1, 90, 80, 70, 60, 50, 30, and then 20 cents. And yes, I've always also experienced 20-cent corn, or 20-cent N. So we've experienced all of that. We've experienced all of what's going to be in the recommendations for prices of corn received. And we've experienced all of that trauma of the really high end prices to, more reasonable end prices from $1 to about 20 cents. That's probably the range that I'll work with for the most part. So the recommendations will be based on that. And the recommendation, that number that the computer program spits out will change depending on the price of corn, and it'll change depending on what the cost of the N is. The higher the price of N, the lower the most economic rate of N will be. The higher the price of corn, the higher the N rate that's economic will be. So it's like that. It's an economic-based and yield-based system for each of those categories, as I explained before. So moving on, these are just some values, and they may change a little bit between now and then, this summer, but I've spent almost pretty much every day working on this since the study began, and so these numbers kind of give you some kind of a flavor about where things are going to be. And these are the gross numbers. You subtract the soil N off of it, any previous crop credit. Any of that stuff gets subtracted off. These are the peak numbers. So in long-term no-till, $3 corn, around 174 pounds of N, and 40-cent N. That's kind of the neighborhood we're in right now, except urea is doing really weird things. But anyway, about figuring 40-cent N, 174, and then $4 corn, 192, $5 corn, and we hope 204 pounds of N. So all of those are reasonable. And each one of those numbers means that it's not that you might get a little bit more corn if you put on a little bit more N, but the take-home message is if you go higher than that with that economics, you're going to lose money doing it. Remember why you put on fertilizer. The reason you put on fertilizer is not so that your supplier will be able to go to Hawaii, but to see if, you know, that you and your spouse go to Hawaii. So that's the reason you put on fertilizer, so you make money. You just don't do it because it's a habit. I hope you don't do it because it's a habit. So these are the high clay sites, and I hope you notice right offhand that the rates of N for each of those is higher than long-term no-till. The long-term no-till is just efficient. That's just the way it is. And so with the sites that have that greater productivity, 223 pounds to 253 pounds, somewhere in that neighborhood. And you go to the sites that are less than 160, and the rates of N are actually higher than that because the efficiency is even less. The yields are less, but the efficiency is way less. And so even though the other ones are higher yielding, they need less N. Doesn't sound a lot like 1.2 times bushels of corn, does it? Okay, so moving on, these are the stars. The medium textures, good drainage, but not too much drainage, good productivity, deep soils, all these things. So here we have ranges of 208 to 232. Not quite the difference in not quite as low as the long-term no-till sites, but they're getting down there. One of the other things I want you to realize on this is that notice the curve. Notice the curves. They go up and then they go down. They're also, but they're not real steep-ish. So that means that they have shoulders. They have shoulders of risk. So there's a range. You know, if you want to risk $1 on this side and $1 on the other side, it's kind of, you know, depending on the model, and this will be defined in the wordage, the narrative that goes out with the recommendations, is that you can go plus or minus 20 to 30 pounds and risk very little economically by doing so. But that comes back to what I firmly believe is most of you have common sense. And so I want to give you credit for common sense, and I hope you appreciate that because it's increasingly less likely that people do that in the world today. So I give you credit for common sense, and I want you to, you know, if you have this range of plus or minus 30 pounds of N, there are situations in farms where through the years you've kind of found where maybe you need a little bit more, and you've kind of found or suspected anyway, but we're afraid to do so sometimes, that maybe you could use a little bit less and you'd still be okay. So, I mean, 117 sites around the region, 77 in North Dakota, and I know that there's people in this room that I've done work on your farm, but I haven't done work on all their farms, and I haven't done work with each one of you in each one of your fields, and it's impossible, but you work with them all the time. And so I want to give you credit for common sense and realize that number is not chiseled on the temple wall, and they won't carry you away in chains if you decide to go a little bit above or a little bit less. So I want you to understand about the shoulder. The shoulder will be defined within and explained within the circulars. All right, who is that guy? All right, so anyway, then we have the problem sites. So why are these high clay sites, especially the ones that have the lower yield potential, what's going on with those? So one of the things I want you to understand is this timeline, and I've talked about this before, that you know, some of you fall apply, and that's okay if you do it late enough, and then the rest of you pre-plant, most of you are in, but you pre-plant the N, you know, corn takes a little bit to come up, and then it takes a little bit in order to get some size where it's really taken on any N of any significance at all. By the time you're about 6 weeks after planting, the corn is only taking anywhere from 5 to 10% of its total nitrogen needs. And so, its demand on the soil is very low. But then the next 3 weeks are incredible. It's not a steady state uptake through the season. What happens is a low uptake, low uptake, low uptake, and then something happens and it starts to grow rapidly. And within 2-3 weeks, it takes up 50% of the corn it needs for the entire season. So if you start out day one and you have wetness, our wettest months are May and early June. And that's the wettest time frame we have, that 5-6 weeks period when nothing's happening. So the nitrogen's sitting around there and transforming into nitrate. And then if you have sandy soils and you get a big rain or a series of rains and it leaches and it leaches and it maybe gets, oftentimes it seems like it gets so deep that the roots can't pick it up when they need it. And then on the high clay side, there's also problems with that too, which is a little bit harder for people to understand. So the high clay sites, leaching is not an issue. In a Fargo soil or something related to it, the movement of water down in the soil is only 0.015 inches per hour, which means in a 24-hour day it's only moving about 1/3 of an inch. So these soils can be wet for a long time. Do I really have to tell you about this? So they can be wet for a long time. Those pores are very small, and in that microenvironment where the bacteria and everything are living and the nitrate is in there, there's this whole suite of bacteria that love anaerobic conditions, and they transform the nitrate to nitrous oxide, which is the same stuff that's in your whipped cream can, if you do something on your sundae, and then into gas. And so all of that is plant unavailable and will remain plant unavailable for probably eons until, some, lightning strikes or somebody puts it through an ammonia converter someday in the future. So it's just lost. It's just lost. It's gone. So that's a problem. So that's the problem with the high clay soils is denitrification. And so I've looked around because I made some estimates in 2010 and 2011 about how much I lost. And so I thought, gosh, did I really say the right thing? I was pretty sure that I was correct, but I went back through the literature and I looked at all different papers where they're talking about denitrification rates. And so the range that's in the literature is somewhere between 1% per day of nitrate and 3% per day for nitrate. So in 2010, when May was wet, the whole month was just wet, and the soils were saturated, not covered with water, just wet for an extended period of time because it rained about every 3 days. And I told people that I thought we lost about 80 pounds of N. So that's about 40% of the total nitrate that was on these plots. And it turns out, if you do the math, that's about 1.3% a day. So that's I feel good. So, and then 2011, we had about 6 weeks, about 45 days where it was even wetter year, if you remember. And I figure we lost about 150 pounds of N, and that's about 1.7% a day. So I think I'm on pretty firm ground on this. So this is a fast process, figuring out about a 1.5% loss per day. If it's wet for a week or 2 weeks or something like that, it makes 20-40 pound difference. If it's wet for a month, it makes less. So let's say that you decide to split your N, and it's side dress time, and then you got to kind of make an estimate about how much loss you have. And I want to tell you I want to explain how hard this is. So these are my campus plots, and that's the end-on data from my campus plots. And this really the end-on data from my plots, because my plots butt right up against the end-on site on campus. If you're ever there and want to see long-term no-till, strip-till, and conventional till on a Fargo soil, you just go between the greenhouses and the end-on station and look for the jackrabbits, and that's my plot right there. So there we go. So in the very beginning, right after planting, we had a big rain. Didn't hurt things. It soaked in. Everything's fine. Then we had another rain, about 1.5 inches, something like that, a few weeks later. And then the big thing, though, is we had 3 inches of rain between about 1 and 2 o'clock in the morning last summer, and I made the mistake the next day of going past the plots on my way to work, which is a real big mistake. And so here are my little flags, and they're just kind of waving SOS, please help me, I'm drowning. And so they were covered with 6 inches of water for a time. So I thought, oh great, so I'm gonna need to side dress some of these, so how much am I gonna put on? This is the plots on that day. About 3 days later, those little ponds out there in the sugar beets and the poor corn over there in the corner, those are the conventional till plots. And and those are like hog wallers. You might be able to see a footprint or two over in the no-till and the strip-till up near the front. These are not compacted plots, they just have incredible structure, and so when it's wet you can walk right across the top of them, and immediately when you go into the conventional plots there's no structure there, you go in up to your ankles, it's a muddy mess, it's horrible, and I shouldn't have to tell any of you, but it is possible to do strip-till and no-till in high clay soils, and I know that you don't believe that, but here we go. So there's 9 years of that going on out there, and the soils are very different. So I figured, since they were saturated with water for a period of time, that maybe we lost somewhere around 40, 50 pounds of N. So when it came time to side dress, I had 3 different treatments out there. One with all the N on early, all the N on late, and then one that had half and half. But I thought, we lost some, so the late probably should receive some more, and in the middle should receive some more, because if I was side dressing for real, that's what I would think about. And so I estimated about 40 pounds, and it didn't do too badly. I certainly had better beets. That circled area down there is the beet yields in the bottom. But the sugar was lower because I put too much N on for the condition. So I shouldn't have planned for so much. So I've spent 40 years in soil fertility, and I guess wrong. And so how in the world are you going to guess right? I suppose just be lucky. Lucky's good. Some of you do good and do well in Vegas. I would do horrible in Vegas, and so maybe some of you just have that natural ability to be lucky. But we got all this kind of stuff going on. So I think we need to look for something else. And so the something else might be inhibitors. So let's think about nitrification inhibitors. And Jay Goose has tested these for a number of years, and some of them do work okay. And so he did some work with 4 different soils. One, of Renshaw, which some of you know. It's kind of a dark-colored soil, sandy loam, usually fairly high organic matter over gravel. There's a lot of that as you go toward Bismarck, around Pendleton, the Pendleton exit. There's a lot of it around there, those irrigated areas over in Kidder County. So then the Glendon and the Bearden, many of you know what those are because you have them on the farm. And then Ulysses is from Kansas, and there's a reason Goose put this in there. We won't go into that right now. So all this is going to be in a journal here very shortly. So we got squiggles. And so we have blue lines up on top, and then the red line, the green line. That's all we're going to talk about, really just the blue and the green, or the blue and the red, because the top 2 lines. So these are different concentrations. The low concentration, about 1 ppm, is about the rate that is on the label. 2 is about double rate, and then the rest are just, to test. So these are incubation studies over a period of a month, and 200 ppm of N was in the pots to begin with. And so the NP, the top line, is for nitropyrin. That's the formulation that's in the N-Serve that you use with anhydrous ammonia. And it's been out since the 70s. I helped to test it when it was in Illinois, when I was in grad school. And so it's been out for a long time. People have used it. It works, and we all know it works. So that did a pretty decent job, and I lost my sheet again. Okay, so they really don't want to see me. They can see me up here. So anyway, the blue line there, even at the labeled rates, we're looking at somewhere around 65, 70% inhibition, which is pretty good. And the red line over there is the encapsulated nitropyrin. That's the Instinct. The encapsulated nitropyrin is called Instinct. They're both Dow products, and it took more of that. It took a really kind of double rate in order to get where the original N-Serve was at the original rate. And then with the soils that have a faster nitrification rate, not all soils have the same rate of nitrification, it took even more. The blue line again, when you get to labeled rates, we're looking at somewhere around 60% inhibition, but it took 4 to 5 times the rate of that with the Instinct. So this is disturbing, because my colleagues and I all thought that N-Serve was N-Serve, and the microencapsulation was great because you could put it on and leave it for a few days. It wouldn't volatilize like the other stuff would. And so, this was a wonderful thing. But my colleagues have had, disappointments. As in the Corn Belt, it's been weather the last 4 or 5 years while they're testing this than normal. And so you would think that the frequency of yield increases with the use of Instinct over not would be very high, but they're not. They're very low. And it's not that nitropyrin doesn't do anything, but we think the reason it's taken, you did it again, The reason we did it again is that it's possible that the nitropyrin isn't coming out of the encapsulation in a great enough concentration at any one time to kill the bacteria it needs to kill. It's a bactericide. It's specific to nitrous ammonium, the stuff that converts. That it's not really doing what it could until the concentration gets high enough with increased rate. So I don't know, but just a disturbing thing. I wanted to share that.
What is that chart supposed to show?
Oh, I'm sorry. All right. So on the y-axis is the residual ammonium in the soil, starting out with about 200 ppm of N. And on the bottom is the inhibitor concentration, and about 1 is the labeled rate, and it goes all the way to 25 times labeled rate. Each one of those lines is a different nitrification product. The top line is nitropyrin for ammonia. The second line down is the encapsulated nitropyrin, the instinct. The third line down is DCD. That's a nitrification inhibitor. It's been around for a very long time, first developed as a fertilizer until they figured out that it inhibited the stage, the bacteria that changed the nitrite, which is the first step in the nitrification process, to nitrate, and so there was a buildup of nitrite, and if you use DCD as a fertilizer at 100 pounds of N, you'd probably kill the corn, and people really don't want that to happen. But if you used it at very low rates, then it's a nitrification inhibitor. And then ATS is something that has a little bit of nitrification inhibiting power that Jay Goose stumbled across a number of years ago, but not enough to even really talk about it.
Does this chart show that N-Serve works?
It shows that N-Serve works, but the lack of performance by the encapsulated nitropyrin, the instinct, is disturbing, because we always thought it was the same, and it's not. That's the big take-home lesson here. Make sense?
Aren't they advertising the second version of that now?
They are, and this is the first version. We don't know what this next one is going to be. But hopefully they'll make incubation studies and be pretty confident that it's going to release fast enough and kill the bacteria. But I just wanted to share that with you. Does that make sense? Sorry. I see these things so often I figure that I can just do this by sublimation or something. All right, so if guessing isn't going to work and the nitrification inhibitors have issues, some of them, then what's the alternative? And the alternative is a side dress, and one of the things we've been working with this project is the use of active optical sensors. We worked with the Green Seeker, developed out of Oklahoma State by Bill Ron and his crew and sold to eventually Trimble, and then the Holland Scientific crop circle sensor developed out of Nebraska from an ex-USDA person there. So we've used both of those at 2 different times, and the long and short of it, because I'm on short leash here, is that there's a relationship in each of these graphs. The bottom line, the x-axis is the reading we get with, in this case, the Green Seeker, but it could be the crop circle, whatever wavelength we're using. And then you divide that by the growing degree days. And dividing by the growing degree days allows it to be used over a period of time and not just exactly, measuring when the 5th leaf is coming out of the world and is a ½ inch long. I mean, life isn't, you can't do that. So dividing by growing degree days normalizes the data so you can make readings on different, over a time period of maybe 10 days, 2 weeks, something like that, and still be on the same curve because you're dividing by the growing degree days. So that's what the curves look like. There's a good relationship there between our readings, and then corn yield is on the y-axis. So what these things do is they predict yield. They predict the corn yield. And so what does that have to do with nitrogen? Well, onward we go. And so here's the example. We'll publish the algorithms for West River long-term no-till, each of the productivities with high clay, medium clay this summer. And so what person would do is you'd pre-program the algorithms that you need for the field. It might be 1 algorithm, or it might be 2. If you have, say, let's assume that you're 20 miles north of Fargo and you have, Fargo, Hegney, something like that, Bearden soils in the field. They're all high clay, all high productivity. You use that algorithm that we developed for those soils, plug that into the sensor and the controlling unit. And so when you go into the field before planting, you want to put on some N so the corn's going to be healthy beforehand. So maybe you elect to put on maybe a third, maybe up to a half, maybe put some N-Surf with it or something, and then you zone the field and put on what you need. And then during that initial pass before planting, also in a representative area of the field, in something like that, it's easy because they're all kind of the same soil category. You put on an area that's about the width of the applicator, maybe about 100 feet long, that has way more nitrogen than you think you're going to need, 200 to 300, whatever you think is appropriate. And so that's going to be your future reference strip. That's going to be the one that you're calibrating against. And so at side dress time, the side dresser goes in, you have the sensor on the front, and then the first thing you do is go on over and you run the sensor across the reference strip. And so that's going to give you the highest yield possible with any nitrogen rate that you can think of. So everything else will be calibrated against that. So what it's doing, when you go into the reference strip, it's doing that. The NC is the reading divided by the growing degree days. That's what NC means. And NC is an estimate of yield. It's a term developed by Bill Ron and his group in Oklahoma. And so that normalization thing. So the reference NC will predict the yield over there. So that's the highest yield you can get no matter what you do with nitrogen. Then, as you go through the field, if the readings are within, say, 5% of that, then nothing happens, nothing turns on. You have enough nitrogen there to do whatever you can do. But then you get to an area of the field where the NC is lower than that, and then it's going to predict a lower yield. And so you have a yield difference. And so with that yield difference, the algorithm at the speed of an electron, about the speed of light, is going to do this calculation, and it's going to do the weight of the corn that's possible with more N times 0.0125, which is a percentage of N that you expect to see in the grain. And then I hope it's not a shock to you, but nitrogen is not used by the plant in the year that it's applied 100%. And so I'll wait for the gas. But anyway, that's always what happens. And so usually in a side dress situation, looking over the literature, if you're putting the nitrogen below the surface of the soil in a side dress situation, your efficiency is about 60%. It's not to the 40% it's lost, it's just being consumed by microorganisms and used in decomposition of organic matter and tied up in various organic forms. That's what's happening, not loss. But anyway, so you divide it by 0.6, and so that gives you the N rate. And so let's give you an example here. So let's say that you go into the field, you put your reference out. Side dress time, you predict 220 bushels on that. And so then you get into another part of the field and it's predicting 160. So at the speed of the light, it's going to calculate 60 bushels times 56 pounds of grain per bushel, and that's 3360 pounds, and then multiply it by 0.0125, divide it by 0.6. And so out of the back of the applicator, as you're moving through the field, during that block of what it's accumulating, sensing, it's going to apply 70 pounds of N. So it's going to do that in blocks. You tell it, how much to integrate, 20 feet, 30 feet, whatever you decide. So these little blocks will all be fertilized differently as the unit is going through the field while you're checking your markets and, reading the paper and watching a DVD or whatever you do out there on the tractor. So this is all automatic. So this summer, we will have print-based, we'll have web-based like the wheat, interactive, nothing to download, it's all on the web. We'll have NREX, basic nitrogen REX, and then also algorithms for all of those categories, all 6 of those.